All right, well, let's get right to it. I'm going to go ahead and pull up the problem set here. Actually, let me share my screen. Here we go. All right, so basically, we got this one here. Minimum number of coins added. Can you see my screen?
Yeah.
Looks good.
So you are given zero index integer array coins representing the values of coins available in an integer target. An integer x is a. Oh wait, that's the second one, right? My bad.
Oh yeah. This is the first that you're
My,
showing.
my bad. My bad. You're given a zero indexed array mountain. Your task is to find all the peaks in the mountain array. This one was like super simple, man. I busted this one out in like 3 minutes. Return an array that consists of indices of peaks in the given array, any order. I think the thing that made it really easy, just a strictly greater. Like both the left and the right had to be less than. So a peak was defined as an element that is strictly greater than its neighboring element. There are some problems like this that it doesn't have to be strictly greater. Like you could have equal for a certain number of elements.
Oh yeah, I think we had that a while ago.
Yeah. And then the first and last elements of the array are not a peak. So you can see in this one, there are no peaks because if the last one was 3, this middle one would be a peak. And then on this one here, you can see, well, the first and the last are never going to be peaks because we don't have one that comes before or one that comes after. So I started on the number 1 and I ended early. And then here I just check the left and the right, and if the left and the right were less than the current element, then I just returned. I pushed that index onto the thing. So just created a output array. I looped over the mountain, created a previous, current, and next just for clarity, and then just checked current against next and previous. And if both of those conditions were true, I pushed I onto output, and I outputted that there. So yeah, that was simple. And then it was funny because I was kind of just like reading number 2, and before I started thinking of any solutions for it, I just checked out 3 and 4 too, which 3 and 4 didn't seem that bad actually. Like they seem just as challenging as number 2 now that I'm looking back, but I'm curious to see what solutions y'all got, if you have any. Did anyone else want to solve number 1? Does anyone else have a different algorithm or a different programming language?
I mean, I was doing something similar in Python, but I think it's similar.
Yeah, you could go ahead and share it if you want.
Yeah, let me paste it in the chat.
Yeah, that's fine. Cool.
How do I do that fancy paste?
You just do the backticks with the programming language. You're doing Python, right? And then put the code in the middle. Backtick, name of the programming language, and then end the code with the 3 backticks too, I believe. Only one, Omar? Would you start late?
No, I take my full time and still only one.
Wow. That's hard to believe.
Oh.
I'm sorry too.
I almost got only one too, honestly. They were tough. The mediums were really tough.
Yeah, you got it here. I'll show you how to format it. So just do backtick, Python, and then paste the code in there. There we go. Alright. For iron range, from 1 to the length of the mountain minus 1. If mountain I is greater than mountain I minus 1, and mountain I is greater than I plus 1, then append. Alright, cool. Yeah, same exact logic. Different syntax. Alright, cool. Does anyone have number 2? I think Fernando said you had number 2, and then Coding Master, you said you didn't get any of the mediums, just the hard.
What? He actually got the herd?
Yes.
Interesting. Did you guys explain the herd already?
Nah, we'll go through the mediums first.
Yeah.
Did you just like skip to the herd one?
The mediums, like I couldn't think of how to do it, so I just skipped to the last one. Yeah.
Oh, gotcha.
You want to share number 2, Fernando?
Yeah. Let me share my screen.
I gotta see this one because I tried so many different things. I tried like 3 different solutions. I think I'm onto something, but man, just couldn't do it.
It's confusing because the subsequence thing implies it's a lot bigger than I think it actually is. And then also it feels like it's dynamic programming, but dynamic programming is too slow. Like there's a bunch of red herrings.
Yeah.
Yeah, I was thinking the same, like using dynamic programming, but these constraints not it's not going to allow dynamic programming solution. So yeah, for the second one, I just I share my thoughts in some part of the comments with this third case. Like you have these 3 coins with the value of 1 and this target, and you will need to add another 3 coins. So I realize when you have these 3 coins, you can start having these possible values like 1, 2, and 3, because when you add these 2, you have 2, and these 2, 3, this the same 3, but you don't have 4, so you need to add this to your sequence, so you don't have 4, but after that you will need 8, but he the this answer is just skipping the 5, 6, and 7, so there is a gap, and you need to cover this. You need to know how to cover this gap, and this is just taking the last element, the last sum that you have, like at this moment you have 3, but when you don't have 4, you're going to add 4, and with 4 you're going to have you're going to reach 7, so that means you are going to cover 5, 6, these numbers. You're going to cover like starting by 4, 4, 5, 6, and 7. So you are going to cover this one. So it's just taking 4 and the last current sum that you have at the moment.
So are you saying that whatever the last thing you could make plus the the newest coin that you had to add, you'll be able to cover everything else in between, and then
Yeah.
whatever comes after is the new. Wow.
In this case is for when you don't have any more coins like this. But if you have more coins, you need to check in. This is other case. But I realized just with this, if I don't have more coins, you just need to add like this. In this case, you are going to add 8. So which is going to which values are you are going to cover with 8? That means it's 7, so plus 8 is going to be 15. So it's like you're going to cover these values like 8, 9 until 15, but you are not covering 16, so you are going to add 16 for the next time. And
So, in the case where you have coins remaining, do you just check which is smaller, like of the next coin versus the sum of the last coin and the new required coin? Or what? What do you do in
in
the other
case,
case?
in case I have coins,
Yeah. So in this case,
yeah,
we got to the end of the list, right? And now we're doing that chain that you're kind of showing with the arrows. But what if like you had got to
like
I don't know,
this.
what if you only got halfway through the coins and you found that make a you couldn't make a number that's in the range.
Yeah, in case you have some coin like this, if are going to start with
Yep.
one, like in this case, if I'm going to start with one, my sum is just 0, and my target, my first target, like is just check if one, we have the value of one. In this case, we can have this value and just increase by one, and this is going to be the last value that you are building. But if you don't have uh, sorry, you are asking if we have this one, so you are going to just increase by one. You have one and you already used this, so the next you need to check for the remainder values. So that means from 4 to 10. I mean 4 and 10 for the remainder coins. You need to drop this coin if you are going to use that. And when are you going to use this coin? It's just if the current element uh, in this range is like greater and or equals this coin value, so you need to use that coin, because in this case, like I need to add, like I don't have two because I used one, but I don't have two is the next one, so I will add two. So we are going to have 3 plus these two, and 3 is already we already have this value, and we don't have 4, so you need to use this 4 value. In this case, you meet this condition, so you are going to increase 4 to 7. So you are using this value in the coin, and you just has one value or one coin left with value of 10. So you need to also iterate every time you are using your coin, and you're going to use that coin when the current element, the value of the current element, is greater or equal to the current coin. So yeah, I also forgot to mention that we need to sort this array of
I
coins.
still don't understand.
Yeah,
Uh,
yeah, that was the tricky part. Just uh, like this, if you are going to cover to 7, so that means you need okay, 8 is not going to be covered, so you need to add 8. That's going to be 15.
so if I'm understanding correctly, we could do the same thing that we did when we reached the end of the array, except that we have to check first that if the next coin
Yeah.
is less than the predicted number for what we
Yeah.
would have to add next. Is that
Yeah. So
I
you're
think
so you're keeping track of the total and the current coin at the same time, and if they don't match up, or if the current coin is greater than the current total, then there's a gap, and you have to insert a coin, basically.
Yeah. If the gap, if the current value is not being covered by this, yeah, by the current sum, and this values goes from one to the target. Yeah. If it's not in the gap, we need to do it. We need to increase that sum using the coins. If you don't have coins, you just need to add this element, like we are doing with this case. We are adding just in this case we are adding just 4, and after we are adding 8. Yeah, when you don't have more coins to check.
Yeah.
But yeah, but if you have, you just need to check if the current element is greater than the coin, because you are going to use that coin if the element that you are searching is less or equal to the coin. Yeah. Like this, you're going to have 15, and the target, if I remember, for this case was 19. So yeah, you're going to cover that. When you reach like it's going to cover to 15, and the target is 19, but you don't have 16. So if you don't have 16, you need to use your last coin. This is 10, so you're going to cover until 25. Yeah, and yeah, you just need to add these two coins. Yeah.
Yeah, that makes sense.
Yeah, I remember I shared something similar. Where was? Yeah, and some comments were like this one. Yeah, yeah, that was the the main idea. This part.
props to getting that done during a contest, dude.
Yeah,
Yeah, thank you. Yeah, that makes sense. So you basically just had a couple variables that you were keeping track and then comparing them on every increase, on every increment. Yeah, that makes sense. Cool, cool. Did anyone else solve number 2? Number 3? I know you got number 4, Coding Master. I don't know if you want to share. I don't know if anyone will even understand it, but you can give it a shot if you want.
I didn't solve number 3, but I feel like it's something with sliding window. But yeah, I can show you guys number 4. Funny enough, there's notes because that was like how I started tackling it, so that helps a bit. Basically, I was thinking about like counting permutations of 10 to the 5 is kind of messed up, or even doing anything that was sort of like dynamic programming related would have been messed up just because it's too big. So it was pretty clear I was going to need to use math. So one way to tackle problems like this I think about is just like, what are simplifications of the problem that I could probably generalize?
Could we just check out what the problem was? I don't know if everyone read it.
Yep.
I skimmed it a little bit.
So essentially we have n children, and some of the children, and they're ordered. So you could think of them as, being in an array, and certain positions in the array, so certain kids are sick. And any kid that's sick can get one of the kids next to them sick. So if you sort of think about like a breath first search, right? They'll kind of spread their sickness out, sort of like a cube, right?
Mm-hmm.
And basically, all of this is jargon for saying on each kid will get sick one at a time, and any of the kids that could get sick might get sick in a single churn, right? So like if we had an array and it was like healthy, sick, healthy, sick, this kid, or this kid could get sick. And so I thought of it in terms of churns, right? It's like in one churn, this kid might get sick, this kid might get sick, or this kid might get sick. And what you're supposed to do is you're supposed to simulate it all the way to the end and count the number of ways in which the kids could have gotten sick, right? So this kid could get sick first, and then this kid, and then this kid, and then this kid, or this kid, and then this kid, and then this kid, and this kid, or this kid first. So all the different orders in which they could get sick until all of them are sick, you're supposed to count. But since that could be really big, you return it modulo 10 to the 9 plus 7.
Mm-hmm.
But does that problem make sense?
Yeah. So there's a couple important variables. One of them is how many kids are actually healthy, and then two is the position of the sick kids, right?
Right. Well, no, this is the number of total kids. So
Yeah.
n is there's 5 kids. The 0th kid and the 4th kid are sick, so they're gonna spread their sickness out. But on any given sickness churn, the kid that's next to this group versus this group might get sick, and you're supposed to count all the possible orders that they could get sick until all of them are sick, right?
Mm-hmm.
So another way to say it is like kids 1, 2, 3, and I think just 1, 2, and 3 are healthy.
Mm-hmm.
So we want to count. So kid 1 could get sick, and then kid 3, and then kid 2, or kid 3 first, and then 1, and then 2, or 3, 2, 1. Those are 3 possible ways. We're supposed to count all of the ways. There are 4, right? So 3, 1, 2, or 3, 2, 1, 1, 2, 3, or 1, 3, 2. Those were the 4 possible sequences. So how can we tackle a problem like this? One thing we could just think about is like, is there a way to simplify it, right? There's 2 things I thought about that helped me simplify it. One was that kids can only get sick if there's a sick kid next to them, right? That's sort of what it says here.
Mm-hmm.
Somewhere. So really, what matters sort of is the contiguous chunks of healthy kids. Does that make sense?
Yeah.
Like, we don't have to worry about the fact that 1, 2, and 3 were the specific kids. We just need to worry about that it was a chunk of 3 kids.
Mm-hmm.
Right?
Yeah.
The other thing was that kids at the end of the array are going to be a bit different from kids that are stuck between 2 sick kids. Right? So this is the first thing I thought of, right? In each second, one contiguous subsequence will acquire an infected person. Right.
Only one?
Right. Yes. So if there's one healthy kid here, and then sick, and then 2 here, and then sick, and then 4, and then sick, one of these in each second, one of these groups, only one of these groups will acquire a sick kid, and we could think of that as like writing that in our sequence, right? Because we're writing with pencil. We're writing down each one, right? Kid 3 got sick. Kid 5 got sick. Kid 7 got sick. We're keeping a record.
Yep.
Right? So as we're keeping our record, we can write down an individual kid, and only one of these contiguous subsequences will go down 1. Right?
Mm-hmm.
So the really simple case is what if it's on the end, right? So like what if it's just a kid that a contiguous sequence of healthy kids, and there's only a sick kid on one side, then the only kid that could get sick is the one on the left side. So the first kid will get sick, and then the second, and then the third, and then the fourth, and the fifth, until we get to the end of the array. So there's really only one way for them to get sick. Same thing on the left, right? There's only one way for these to get sick. There's only one way for these to get sick. Does that make sense?
Mm-hmm.
The other thing was, okay, so how do we think about the number of ways that a single chunk can get sick before we worry about combining the chunks, right? So I have 5 sick kids, and they're stuck between 5 healthy kids, and they're stuck between 2 sick kids. How many different ways could these 5 kids get sick, right? So if it was just one, it'd be one way. If there was 2, the left could get sick first, or the right could get sick first. So there's 2 ways, right? If there's 3, the left could get sick first, and then there'd be 2 remaining, or the right could get sick first, and then there'd be 2 remaining. There's a pattern here, right? The left or right could get sick, and then we have n-1 left.
Mm-hmm.
That's recurrence. We have number of ways it could get sick. If it's a chunk of 1 is 1, and if it's n, then it's going to be 2 times num of n-1.
So it doubles.
And yep, this recurrence right here is just 2 to the n-1, right? So then the thing to think about is how do we combine separate groups of healthy kids, right? Because not only could the left or right of this group get sick, but the left or right of this group could get sick, or the left or right of this group could get sick, and we have to sort of interweave them all together and count all the ways we could do that. So I don't know if you guys ever heard of bars and stars, like if you've taken like a combinatorics class, but like the simplest way I tried to think about it was, what if there's just 2, right? One has size M and one has size N. Well, we know all of the kids are going to get sick, right? So like if there was N1, N2, N3, N4, N5, and then there was M1, M2, M3 or something, we're going to write down all of these kids in our sick sequence, right? So really the question is just for each time we write it down is, because we know the number of ways to order the group of N and the group of M. Now the question really is just how many different ways are there to write down N and M together, which is how else can I describe that?
And N and M are healthy and sick kids, right?
No, so N would be one group of healthy kids
Yeah.
that are stuck together, and then M would be a different group of healthy kids that are stuck together. So this is 4 healthy kids stuck together, or I mean 5, and then this is 3 healthy kids stuck together. So you can imagine there's a sick kid, surrounding them.
Yep.
Yep. We know if it was just N, the group N, that there'd be 2 to the 4 ways for them to get sick, right? Because there's 5 of them. We got this. Same thing with M. We know if it was just these 3, then there would be 4 ways for them to get sick. But when there's both of them, what's possible, right, is that we could have N1 get sick, and then M1 gets sick, and then M2 gets sick, and then N2 gets sick, like that. You get what I'm saying?
Mm-hmm.
So what we think about is we could think of like maybe each kid in N is a star, and each kid in M is a bar, and we think about all the different ways that we could write sequences of stars and bars.
Mm-hmm.
Does that make sense, right? So this would be the number of kids in M plus the number of kids in N. That's the total number of symbols that we're going to write, right? We're going to write all these kids' names plus all these kids' names. So we sum them, and then the number of ways in which these can vary is going to be the number of ways that we could choose the N kids from the M plus N total kids, right? So like if you've ever done unique paths, this is just like unique paths, right? Like what's the number of ways you could get from the top of the grid, top left to the bottom right, by moving right or moving down, right? We're going to have to move right a certain number of steps and move down a certain number of steps. And along the way, we can choose in different places where to step. But so this like has a formula, right? M plus n choose n. Does that make sense? Like how I got that?
Yeah, yeah. Does
Yeah.
it make sense to everyone else?
Yeah, sounds like discrete mathematics.
Yes.
Yeah.
So then to generalize this because there's going to be a bunch of groups, right? It's not just M and N. We're going to have M and N and O and P. So to generalize this, there's a formula, which is that we take the sum of all of them, factorial, and we divide by the individual factorials of each one. This is how you count all of the ways. So if you have 5 kids in this group and 3 kids in this group and 7 kids in this group and 2 kids in this group, you would add up, those numbers, factorial, and then you divide by the individual factorial of each of those numbers. That's the number of ways that you could write down the kids' names from each of those groups if the kids in the groups are indistinguishable from one another. Use this formula. And then the only other thing is that for each group, we need to multiply it by the number of ways to write each of the kids' names. So we treat each of the kids as indistinguishable, and we introduce their names mattering by multiplying by this. So then the question was just, how can I do that and keep the answer correct? Because this number right here could be up to 10 to the 5, right? And I can't do 10 to the 5 factorial because that's going to take my computer like the age of the universe or whatever. You know what I mean? So I almost messed this up because I forgot about modular inverses, but so that's what this is doing, right? I count the kids on the left, count the kids on the right, I count the healthy streaks of kids, and put them in a list. I start with my total at 1, and I start with that factorial, and I take the modulus each time. So I'm working in the finite field. That's what you call it, right? When you're doing all of your arithmetic in the numbers from 0 to n, you call that the finite field of n, right? It's usually like a big F with like a little subscript n. So I keep myself in the finite field that is mod, which was 10 to the 9 plus 7, right? I find this factorial. You're wondering why I did this. It was because before I was doing this, I was doing division, and I was trying to minimize divisions. But so I think something that would work just as well is if I got rid of this. And then over here, I said for streak in left, right, streak like this, but only if streak. So if not streak, we're going to continue. Okay. I think this will be a little bit more understandable for you guys because the other thing was just like an optimization I had made because it was like timing out. Make sure it's still running correctly. 4-3. Yep. Okay. So I find the factorial. That's what this is doing. Then I go through each of those streaks, and I find the 2 to the n minus 1, but in finite field of mod, so that way I don't break anything. And then instead of dividing out, so you notice here I have division for these factorials. When you're working in the finite field, division is still going to land you on another element in the finite field, right? So if we were working in F7, let's say, right? Our numbers would be 0, 1, 2, 3, 4, 5, and 6. Those would be all of our valid numbers. When I divide let's say I want to find what is 14 divided by 3, but mod 7. What does this give me? This gives me 14 divided by 3, that's going to be 12. And then 2. I think it gives you 2. Something like that. I don't even remember right now. My point, though, is like... Here, this will probably be easier. We have 21 divided by... I want something that's not 0. What's 3 times 3? 9. Okay, what's 9 divided by 3 mod 7? It's 3, right? But if I wanted to land at 3, the other way I could have done it was I could have said... Because what is 9 mod 7? It's 2, right? So now we get confused. What's 2 divided by 3 mod 7? Ooh, this is kind of icky. If I ask Python to give me 2 divided by 3, I'm going to get 0, right? If I'm using, like, this division. So what we notice is that there's a number which we can multiply 2 by to get 3 mod 7. Right, so going back to this, we have 9 divided by 3, that's 3. What could I multiply 2 by so that when I take the modulus of it, mod 7, I get 3? I think 2 times...
Five.
What's something times 2 times 5? Yeah, 5, right? So in the mod 7 world, multiplying by 5 is equivalent to dividing by 3. It's called the modular inverse. Does that make sense though, right? I take 2 times 5, that gives me 10, mod 7, and I get 3. That's the same answer as the 9 divided by 3. So this allows me to keep my answer correct without having to actually do division. I do multiplication by the modular inverse. That's what I'm doing here, right? For each of those little, I had looked that up too. I asked ChatGPT, I was like, how do you make it right? Because I forgot. These little factorials, instead of dividing all the factors, I'm multiplying the modular inverses of each of the factors. And all I'm doing for that is I'm just saying what's pow of n to the minus 1 in the mod finite field. And then for the streaks, I do the same thing where I divide out all the possible ways to order it, but I don't multiply by 2 to the n minus 1 because remember we talked about if it was just like 5 healthy kids, only the one on the left here could get sick each time and not the one on the right. So I don't do that part. I just skip that for the left and right. And that works. Like you get 4 and 3, I think. I don't know if this would be too slow or not. It might be too slow because of the change I made. Nope, it worked.
Nice.
Yeah. I don't know if that made sense though.
Yeah, now that made sense, and then you have the edge case for the left and the right because it's just different than if it's a group that's in the middle, basically.
Yeah.
Yeah,
I think I think the implementation is really actually not that bad. I think the harder part was just like thinking of the discrete math.
Yeah, no, this one's almost easier than number 2.
I mean, I got this one and I didn't get number 2. Right? Like, yeah, because I agree. I would say this one's easier than number 2, honestly.
Yeah, it made sense. It made sense for sure. I mean, they both made sense. Fernando, your solution made sense, and your solution made sense as well. So, yeah, they both made sense. Yeah, they were all pretty tough today. It's all good though. Nice. Thank you.
Yeah.
Cool. Does anyone else have one that they want to share before we sign off? John S.
Does anyone get the third one?
I sure didn't.
All right, cool. Thank you. If anyone's interested, actually, we're doing a data structure algorithm Monday through Thursday now too. I basically just post. I'll share my screen really quickly so everybody could see. Basically, what we're doing is, if you go to Problems of the Day channel, I just post 4 problems Monday through Thursday, and then we meet at 9 p.m. 9 p.m. I think it's 6. I think it's 8 p.m. Yeah, 8 p.m. we meet, and then we meet from like 8 to 9 and just share as many as we can. Basically, we've been pasting the same hard ones all week. Last week though, and no one got to the hards. But yeah, we're gonna be
Oh, are
doing
you guys
this.
posting the solutions and then like updating them as people find them?
No, I'm posting the problems during the day just so people could work through them during the day when they have time, and then we're all meeting at 8 o'clock and just sharing the solutions we came up with.
Right, so that's why the hard stayed, because no one shared solutions for them.
Oh yeah. Yep.
Also, I feel like people here would like appreciate advent of code. I don't know if everyone here is aware of it because I wasn't for a couple of years.
Yeah,
But
Cassie posted it in. Yeah, Cassie posted the Advent calendar coding challenges during December, right?
Yeah.
Yeah, she posted
So it's
it.
in like 15 minutes. I'm gonna try and get on that leaderboard. I'm gonna make it happen one of these days.
Nice. I know. I can't wait for the day comes where we solve all 4. Come on, boy. All right, cool. Thanks everyone for popping in tonight. I will chat with you all later.
Peace out.
Peace.